From Hooke's law, we are aware about the modulus of elasticity. The modulus of elasticity is the constant of proportionality that is introduced in the Hooke's law. That is, when stress is directly proportional to strain, stress is equal to modulus of elasticity into strain, which has been already discussed. Now we have got moduli of elasticity. We have got three moduli of elasticity. One is Young's modulus, second one is Bullock modulus, and third one is modulus of rigidity or shear modulus. The Young's modulus is defined for solids only, and it is the ratio of normal stress to longitudinal strain. That means when a cylinder of length L is pulled by a normal force, an extension is produced that is equal to delta L. So this delta L is produced in a longitudinal way. That means this is longitudinal strain, or this is increase in length. So Young's modulus is defined as the ratio of normal stress to longitudinal strain. So we can say that Young's modulus of elasticity is equal to normal stress divided by longitudinal strain. We know that if the radius of this cylinder is r, so normal stress is force per unit area, the force is F, area is A, the longitudinal strain is increase in length is delta L, the actual length is L, so the strain is delta L divided by L. Now we are having the area of this circular section of this cylindrical rod, so the area of this base is pi r square. So this equals to F by pi r square divided by delta L divided by L. That means the Young's modulus is equal to F into L divided by delta L into pi r square. This is the Young's modulus of elasticity. The Young's modulus of elasticity is the ratio of stress and strain. So the Young's modulus has got the dimensions and the units of stress, as the strain is dimensionless and unitless. But remember this, the Young's modulus is only applicable for solids, not for liquids and gases, because in liquids and gases there is no longitudinal strain produced. Talking of Bullock modulus, the Bullock modulus is applicable to solids, liquids as well as gases, because upon the application of normal force there is decrease in volume for solids as well as liquids as well as gases. That is, solids, liquids and gases all have got Bullock modulus. Now in this case, we have a body of volume V on which normal force is applied. At the normal force is applied, there is a reduction in volume. The reduction in volume is equal to delta V. So this part has got the volume of V minus delta V. Delta V is the reduction in the volume. So the Bullock modulus of elasticity is defined as ratio of normal stress and volumetric strain produced. Now the volumetric strain produced here is taken as negative because there is decrease in volume. Volumetric strain is given as the ratio of change in volume to original volume, but the sign is minus because there is reduction in volume. So we can say that Bullock modulus of elasticity is equal to normal stress divided by volumetric strain. So B is equal to F divided by A, and volumetric strain is equal to minus delta V by V. As already discussed, minus sign is because there is reduction in volume. So we have B is equal to F into V divided by A into minus del V, that is minus F into V divided by A del V. Now the solids, liquids as well as the gases have got the value of Bullock modulus. The value of Bullock modulus B is higher for the solids, lower for the liquids and lowest for the gases. It can be best understood when we talk of compressibility. Compressibility is defined as the inverse of bulk modulus. That means if the bulk modulus is high, the compressibility is low. If the bulk modulus is low, the compressibility is high. We know that solids are less compressible than liquids than gases. That means when we talk of gases, their compressibility is more, that gives us their bulk modulus is less. When we talk of solids, their compressibility is less, reduction in volume is less by the applied force. That means their bulk modulus is high. As K is less for solids, B is high. So the bulk modulus for solids has the highest value and the gases has the lowest value. When we talk of rigid solids, the bulk modulus and Young's modulus has got the value of infinity. How can we say the Young's modulus or bulk modulus of a rigid body is equal to infinity? We know that a rigid body is a one that suffers no change in the length or no change in the volume by how much the force is applied on it. It doesn't depend upon the force. The rigid body doesn't have any extension or doesn't have any change in volume when the force is applied on it. That means delta L is equal to 0 for rigid bodies and delta V is equal to 0. When we talk of Young's modulus is equal to F into L divided by delta L into pi r square. As for rigid bodies, this delta L is equal to 0, change in length is equal to 0. So Young's modulus for a perfectly rigid body is equal to infinity. When we talk of the bulk modulus, again for the rigid body, the change in volume is equal to 0, and when the 0 is in denominator, this term becomes infinity. So bear in mind, the Young's modulus is applicable to solids only, the bulk modulus is applicable to solids, liquids as well as the gases. Talking of the modulus of rigidity or shear modulus, this modulus of rigidity or shear modulus of elasticity is applicable to solids only because a liquid at rest cannot sustain a tangential force. That means, like Young's modulus of elasticity, modulus of rigidity is applicable to solids only. Now, what is the modulus of rigidity? The modulus of rigidity is given by G. The modulus of rigidity is the ratio of tangential stress and shearing strain. That means G is equal to tangential stress is F divided by A, force per unit area, and shearing strain is equal to theta, as it has been already discussed in previous lectures. Now, this theta, when we talk of the displacement of the top surface as delta L and the length of the side as L, this theta is equal to delta L divided by L. So we have got the shear modulus of elasticity or modulus of rigidity equal to F divided by A divided by delta L divided by L. That is equal to F into L divided by A delta L. As the shear modulus of elasticity is the ratio of stress and strain, so like Young's modulus of elasticity and bulk modulus of elasticity, the units of all the moduli of elasticity are equal to the units of stress and their dimensions are same as that of stress. Bear in mind. Now, mainly, modulus of rigidity has got a lower value than the Young's modulus of elasticity, and in general, G is equal to 1/3 of Young's modulus of elasticity. Thank you.